Good afternoon. Anybody have any admin or logistics questions? I have one small admin logistics announcement, which I had warned you that this whole middle part of the course is very mixed up and confusing for me because between COVID and last year, I team taught with somebody else, plus trying to get some new material in. This year, it's not going to be the exact same sequence of topics as ever before. And I kind of found out this morning what I plan to do next week really doesn't work because I had forgotten that there was something else that has to come first. So I have only just as of late this morning put up onto Canvas the material for Tuesday, but Tuesday is set. Thursday is still not set. I have updated the schedule, but so you'll want to look at the updated schedule or the Canvas page, but it'll get updated one more time. And it's not going to happen right away because I got to go to the Middle East this weekend and I will not get to this until after I get back from that. So I'm running just in time on getting materials ready and I apologize for that.
You're going to the Middle East this weekend and you'll be back for class. Is that what you just said?
Yep.
Okay, just casual.
I so miss COVID. COVID was fantastic because I did not have to live on airplanes and I'm back to living on airplanes and I don't particularly like it. Any substantive questions? Okay, so the game plan for today is really only 3 ideas. The bad news is they're all really hard to wrap your head around. So we're going for a relatively small number of topics and hopefully there'll be time for it to sink in. The first 2 are really very important. The third one, yeah, it's nice to know, but if you don't get that, that's really not a problem. So this first crucial and hard idea is the difference between the confidence interval for a single outcome and the confidence interval for a mean. I said very clearly on the first day of class, anytime there's uncertainty, you don't want to give only a single number, right? That was that story about forecasting this flood. The National Weather Service said 49 feet flood stage. The levees were 51 feet tall, so nobody did anything. Lots of people died. They should have said 49 plus or minus 9 would have been better. So you know you want to give these intervals. And there are 2 kinds of intervals that you can give or that pop out of Monte Carlo simulation results. It's really important to keep track of what each means and when to use which. So that's this first idea. Now, one kind of interval is captured on this slide. And it comes with a really cool formula. It looks like if you use this formula, you'll be smart because it's got like this plus or minus 1.96 times something. And that kind of reminds you of statistics class. So it must be hard. It must be good. This is probably not the one you want to use. Okay. This one is the confidence interval reflecting your limitations on your knowledge of the center of that distribution. Right, so there's a distribution of what's actually going to happen to you and your organization. And you want to pay attention to that whole wide distribution. You want to be ready for it. This is not that. That distribution has a mean, you know, that fulcrum that would make the board balance, and you won't know that mean exactly. You know, visualize the simulation, get 10,000 trials up at the top. There's a cell where you do average of the 10,000 trials. That cell will wiggle every time you press recompute. It'll move around a little bit. The formula up there really just has to do with how much that cell is wiggling. So it's not telling you the range of things that could happen. It's just telling you how precisely you know a single number. And the giveaway that this really isn't capturing risk in the real world is the fact that the fancy formula has out there a divide by the square root of n, and n is the number of trials you run on your computer. When you run more trials on your computer, you improve the precision of your understanding of the uncertainty. You don't actually reduce the amount of uncertainty. You don't reduce the risk that your organization faces. All you do is improve your understanding about some aspect of that risk. Here's my metaphor for that. There is uncertainty about what the weather is going to be this weekend. If you watch a weather forecast, will that change the weather? What will it change? It changes your knowledge about what that weather will be, but it doesn't change the weather. If you watched 10 different weather forecasts on 10 different channels, would that improve your understanding? Yes. Would it change the weather? No. All right, so the fact that there's an N up there and the N pertains to what you're doing on your laptop, that should be the giveaway that this confidence interval is not about the risk that your organization faces. This is just a confidence interval reflecting the precision of your imperfect estimate of something. Specifically, in the middle of the slide, the center of the distribution, the bottom of the slide, the probability of a particular outcome. Yeah, I'll skip this. So that's what I basically said. Cranking up trials improves your estimate of a parameter, but it doesn't change what's actually going to happen. Here's my other attempt to try to communicate the idea. Takes advantage of this 20-sided Dungeons and Dragons dice courtesy of my son. Suppose that our organization's future depends on the result of a single roll of this die. This will be like driving our revenue or the number of lives we save or something important. But we're only going to get to roll the die once, and the result of this die roll shapes the future. And our job as analysts is to prepare our boss for the result of this one roll of the dice. And we get to run a Monte Carlo simulation. What are we going to tell the boss? Now, what we would most like to tell the boss is, here's the distribution, right? But we work for a dumb boss. The boss cannot read the distribution. The boss says, just give me a range telling me what I should prepare for. All right. Now, we're going to look at the Monte Carlo simulation result in a minute, but this reality is so simple. We know what the right answer is going to be. We know what things are going to be, but then we'll look at what it looks like in the Monte Carlo simulation so you can make the connection. All right, so when I roll a 20-sided die, that is the probability mass function for the result. It's just like a 6-sided die, except now there's 20 bars instead of 6. So what is the real mean of that distribution? But the mean of a regular die is 3.5. The mean of this distribution is
1.5.
exactly correct, 10.5. What is the chance that when I roll this, I'm going to roll a 10.5?
0.
It's never going to happen. If we're going to give a 90% confidence interval, balanced 90% confidence interval for the result of the die roll, the balanced 90% confidence interval is one where 5% chance reality is below it, 5% chance reality is above it. What should we tell the boss?
Between 2 and 19.
Exactly. All right. So that's for real how this is going to work, because this is so simple. And by the way, we'll see what. Okay. Roll the 2. So if we had said 11.5, we would have been fired. If we said 2 to 19, we would have kept our job, barely, but we would have kept our job. Now let's see what the simulation results look like. And so you can see which portion of the usual simulation display you want to pay attention to for what purposes. So here's my model. The whole model here is very, very simple. I have replicated it 10,000 times. I've frozen it because there's something on the next sheet. I didn't want to have two sheets going on at once. But this is the standard display that you get from that template I gave you. Here is the average and standard deviation of those trials. And I found this out in the other class. For whatever reason, I have the 95% confidence interval here. I really want the 90%. So let me just change the constants there. Okay. That range is the range that comes out of the fancy formula. Right? That's fancy formula. Sample mean minus 1.645 times sample standard deviation divided by the square root of n. That is that thing. If I reported that range and then the world gave our organization a 2, what happens to me?
Fired.
I'm fired. Right? So don't use that range to capture the risk that your boss should be prepared for. Where do you find the range 2 to 19? You look at the percentiles, specifically the range from the 5th percentile to the 95th percentile. And that percentile function does just what you would expect it to do. You give it the 10,000 numbers and you give it the percentile you want, and it kicks out the value on the horizontal axis that goes with that percentile. So if the distribution was shaped like that, then that value is about the 5th percentile. That value is about the 95th percentile, since 95% of the stuff is below it. And that's the range you want to tell your boss if your boss can't see the whole picture and will only listen to a range. Questions? Feel free to ask them. This is one of those where, and once you get it, but until you get it, it's hard. And this is not an easy distinction. I know from having taught. Yep.
So like these percentiles, we would label these as like just a confidence interval, like range. Is that how we would label it?
Yeah, you would tell the boss 90% chance that the outcome will fall between 2 and 19, with 5% chance of being below and 5% chance of being above. There are instances in which you want to do a one-sided confidence interval, but they're kind of rare in management. Usually in management, you want the balanced interval. And as a quick aside, if I ever ask you on a homework for just an interval, I mean balanced, even if I don't say it.
Wouldn't it be equally correct to say there's a 90% chance it would fall between 1 and 18?
Yes, that's just not balanced. That's the one-sided interval. And like I said, we can cook up managerial applications when the one-sided interval is in fact what we want. In fact, in finance, there's this notion of value at risk, and that is entirely one-sided, where you're saying, I don't need to protect against unusual surprises in the positive direction. I'm only interested. So yeah, sometimes you'll be interested in a one-sided interval, but my questions I'll ask for the balanced. All right, if that's clear, then we come to the exception. When is it you would actually be more interested in this?
Is this when you would do something repeatedly? I think in the reading, the example was surgery outcome or something like that.
Yep. If your organization gets to roll the dice 5,000 times, then you do care about the average result. So what I just said is when the model you built is modeling what you will experience. But if what you've done is built a model of just one replication and the organization will experience 5,000 replications and the boss is interested in the total, then you care about the mean. Because in that case, the total is going to be equal to the sum. I'm using 5,000 to indicate a large number that's not 10,000. I'm using 10,000 for the number of trials. This is not the number of trials. This is the number of actual employees you have, number of surgeries you're going to run, or whatever. And by definition, that's just equal to 5,000 times the average. And now you care about how precisely you've estimated that average. If I'm facing that situation, for real, John Calkins, which interval do I use? Neither. Because I still think that the second interval confuses people a lot. But what I would say in that case is, boss, look, it's going to be 5,000 times 10.44. And if the boss says, are you sure it's exactly that? I would say, no, you're right. It could be between 5,000 times 10.34 and 5,000 times 10.53. But that's really not, it's not very often that that range is a range that's going to make one want to make a different decision.
So in the case with the flooding, since we didn't, like, that's not something that would occur again and again and again, would we be more interested in giving people a percentile range then?
100%. So like, this is your, the model is the model of all of the rain and the evaporation and the wind and the amount that's absorbed into the ground and so on. And then you run that 10,000 times to improve your understanding of the distribution. And then that is what you tell the people in Grand Forks, North Dakota. And exactly, the National Weather Service didn't. The National Weather Service just said this, but if the National Weather Service had said that, it would not have helped. That would have been the National Weather Service saying, our best guess is 49 feet, and the precision of our best guess about the average is the average is between 48.8 and 49.2. In some sense, that's almost worse. If you just say 49, at least you haven't lulled people into thinking that they've been given a range. But if you say 48.8 to 49.2, then people could be forgiven for saying, oh, I guess that's what I need. That's the range I need to prepare for. It's not. Okay, let me just show you this third sheet. It may help with this understanding, or it may not, but we'll give it a shot. So what's going on this sheet? I am going to generate a bunch of these dice rolls. And in particular, over here in these rows, there are going to be a roll of 400 dice. And I can take the average of those 400. I can take the sample standard deviation of those 400. And then I can do the funky fancy formula for the lower and upper limit on the mean as I estimated based on that Monte Carlo simulation with 400 trials. And then this variable is the interesting one. This is an if statement that says, is the true mean, which I know is 10.5 because you told me so, if that 10.5 is bigger than the lower limit and also lower than the upper limit, then I'll write a 1 and say, hooray, yes, correct. That formula did embrace or encompass the true value, and 0 if it didn't. So in this case, that range does cover the 10.5, and it'll take me a while to find one that didn't, so I won't, I'll try a couple times, but if it doesn't, good. Now, that particular draw of 400 happened by bad luck to have an average that was so high that the range did not include 10.5, and so the cell is a 0. Now, over here, I'm gonna run that 1,000 times. So now when I press recompute, I'm actually doing 400,000 rolls of the dice. But I'm doing 1,000 batches of 400 rolls. And this key outcome is for a given batch of 400 rolls, did the confidence interval include the actual value of 10.5? And for this 1,000 replications of 400 rolls each, 907 did have that formula encompass 10.5. So that's the meaning of that interval. It's not telling us the range of what happened. It's giving us a sense of how precisely we have estimated the unknown center of the distribution with our Monte Carlo simulation. Okay?
What you just talked about, that confidence interval, what do you compare that to? And so you run it and it tells you of those 1,000 samples, what percentage of them encompass
10.5.
10.5? Is that just for our knowledge, or do you compare that?
I'm trying to persuade you that the formula works. So of these 1,000 instances, pretty darn close to 90% of them had the formula encompassing the 90.5. So the formula is well calibrated, to go back to that language you used in the first day of class. The formula is not systematically overconfident. Their range isn't too narrow or too wide or whatever. So the formula is doing what it purports to do. That's just not what we usually want to do when our model is a model of what we will experience once. All right, that's the first really big idea. The second big idea, I think, is best learned by doing the case. So that's why I had you read the imaging department case. So someone want to summarize what's going on in the imaging department case. And by the way, this is totally inspired by teaching the the Masters in Medical Management doctor executives. Yep.
Yeah, I was gonna say in the imaging case, there's like 3 different solutions that they're running into an issue in which they are not maintaining their revenues, they're losing money. So they're like, the simple solution is that when we have too many, when we're overbooked, we'll just have overtime for our workers, work them overtime and essentially address those. But they're running into like law of diminishing returns a lot of the times, in which they're so overbooked that they're still losing money, and then they have the costs of the cost of turning individuals away because they're not able to see them, so they're losing in that regard, and they need to find a solution.
Yep.
Yeah.
I mean, let's back up. The big picture of this is a year ago, they didn't have the imaging machine. And they did some budget forecasting to figure out, could we break even? And by the way, this is exactly how hospitals often think about these purchases. They operate on very thin margins. They don't expect to make money on a lot of these technologies. They do them for reputational benefit, but they also cannot afford to lose money. So they're very sensitive. Should we invest in this expensive thing? Should we hire this super duper surgeon? We've got to at least break even. So way back a year ago, before they had the machine, they did some forecasting, and that budget analysis said, yeah, we're going to break even. So then they bought the machine. Are they in fact breaking even? No, they're losing money big time, which means all of the people we're sitting with in this conference room, including us, we're about to lose our jobs because the hospital will just axe something that is systematically losing money, cannot afford to have negative margins. And an observation is we're not capturing all of the revenue because we're turning patients away when we have more patients than we have capacity. So the fix that's proposed is, let's have the clinician portion of the staff work overtime until we have captured the revenue from all of the patients. So we're never turning away any of the patients. And capturing the additional revenue will help us amortize the fixed cost of this expensive machine over a bigger book of business. And hopefully that'll fix the problem. The basic facts are things like equally likely to have any number of patients between 5 and 15. So the average is 10. 1 day out of 5, the machine breaks down for half a day. This is revenue per patient, cost of labor, cost of machine, yada, yada. A year ago, when they forecasted those things, how accurate did those forecasts turn out to be? Are they losing money because they forecasted these quantities incorrectly? Forecasts were exactly correct. In every respect, all those parameters turned out to match exactly what they budgeted. So the problem here is not unrealistic forecasts. Let's, this page is how they thought 1 year ago. So 10 patients on average, that would be $10,000, but the machine is going to be down 10% of the time. So we're actually doing an average $9,000 in revenue, and our cost will be $9,000. So we're cool. The $9,000 is $3,000 in amortized capital costs, $6,000 in labor. They're not cool because they are not actually capturing as much revenue as they thought. So the new idea is, even on days when the machine breaks down, we will keep the clinical staff until every last patient has been seen. And now we're absolutely rock solid guaranteed to average $10,000 in revenue per day. Our costs are now hard to figure out. We still have the 9,000, but we have to have some overtime costs. But that is genuinely uncertain because the number of patients varies, whether the machine breaks down varies. So they can't figure that out, but they thought about the worst case. And the worst case analysis is here. All right, so the worst possible day for overtime cost is 15 patients and the machine breaks down. So you can only treat 5 patients before 5 p.m. A full batch of 10 patients has to be treated after 5 p.m. That's an entire shift. Blessedly, by sheer coincidence, 2/3 of the labor cost are clinical, 1/3 office. The clinical who stay after get paid time and a half, 150% times 2/3 cancels. What do you know? That's great. Yeah, so I rigged it to make that simple. So the overtime cost for a full shift of 10 extra patients would be another 6,000, i.e. 600 per patient. And in that scenario, we've got the original 9,000 plus 6,000 in overtime labor cost. Cost is 15,000, revenue is 15,000. So in the worst case, we break even. If the worst case is break even, on average, we got to be okay. Put yourselves in that conference room with the clinicians. You've just heard all of that. You're supposed to be the super smart Carnegie Mellon grad school graduate. What do you say? And I'll sort of preempt a couple of things. The other section, people said very reasonable things like, oh, if we push labor that hard, there will be strikes and work stoppages, or patients won't actually stay that long, so they'll leave on their own. Those are very reasonable things to wonder about, but they're not the point here. So you have to trust the clinicians that the patients will stay until 11 p.m. Yeah. No?
I think I was still stuck on the topic one.
Well, we can go back to topic.
Because I was gonna say, wouldn't you still need a range for the worst case scenario? Like, this
Well,
seems too
sort of
exact.
the definition of the worst case is the very end of the distribution. We're in a week where the tool you're supposed to be learning is Monte Carlo simulation. So what do you guess is the right thing to do? Build a Monte Carlo simulation. Yeah, and then see how it plays out. In some sense, you're watching people try to reason about probabilistic situations with their intuition and seat of the pants judgment. There should be a red flag up right there. And for real, when this happens, you want to like go build your little Monte Carlo simulation on the side. Sometimes you're going to say, yeah, they got it right. And then you've just done some extra work and you keep quiet. And sometimes you'll discover, nope, there was some place where that intuition got tripped up, and then you're the hero. So what does a simulation look like? All the stuff up on top is basically just parameters of the problem. There are things like $1,000 in revenue per patient. If the machine is down 10% of the time by going down for half a day at a time, then that means it's going down 1 day in 5. So that's that little calculation. And this is the calculation that I alluded to. If you had to do a full shift of overtime, that's $6,000 for 10 patients. Overtime cost per patient is $600. But up on top, that's really no moving parts up there. That's just facts and parameters. Here are the moving parts. These two cells wiggle. They move around. This cell is how many patients show up. So it's ran between 5 and 15. This is whether the machine goes down. So it's just an if function like we used on Tuesday. This is a Bernoulli outcome because the machine's either up or down. So I generate a random number between 0 and 1, compare it to that 20%. If it's less, then I say, yep, the machine went down. Otherwise, it's fine. So those are the only two random variables in this model. It's actually a pretty small simulation model in terms of number of random variables. Here, I'm computing some intermediate quantities. Yeah, this is good. This cell is the capacity to treat patients before 5 p.m. So I'm just translating that binary outcome, fails, works, into either 5 or 10. So if the machine goes down, I can only treat 5 people before 5 p.m. If it doesn't go down, I can treat 10 before 5 p.m. This is the number of people that I actually treat before 5 p.m. It's the smaller of the number of patients and my capacity to treat people before 5 p.m. On this particular day, 13 people showed up. My capacity to treat before 5 p.m. is 10. So I treated 10 people before 5 p.m. On this day, only 6 people showed up. So I only treated 6 people before 5 p.m. This is the difference between the total number of patients and the number treated before 5 p.m. That's the number who are treated after 5 p.m. by overtime, if I'm going to do overtime. And then I just multiply that by 600, and that's my overtime cost. And then over here, I have my two policies, the original policy and the new policy, revenues and cost. If I don't do overtime, my revenue is $1,000 times the number of people who can be treated before 5 p.m. I don't get any revenue from the other people. They've gone to a different hospital. And my cost is just always exactly $9,000. There's no overtime involved. And net revenue is just the difference. If I do the overtime strategy, revenue is very simple. It's just number of patients times 1,000. It's the cost side that's more complicated. I've still got that base 9,000. But then I have to add in cell C19. Net revenue as before. This is a simulation, 5,000 trials. I'm just pulling those things over from the previous slide. And that's the histogram. It's chunky because the outcomes are discrete. Where is the mean of the yellow? Yeah, bad news, right? You know, there's a big lump there at plus 1,000, but there's a whole bunch of stuff to the left, including way to the left. So it was bad news before. Where is the mean of the blue? It's better. But it's not quite there. So we used to be losing 1,100 a day. Now we're losing 300 a day. We still lose our job. We were told 0 was the worst case if we use overtime. That's worse than 0. What happened?
Did we mistakenly use the sample mean and not do a range in terms of the worst case scenario?
The concept of worst case is supposed to be, it literally is the worst it can possibly be. So it isn't really supposed to have an interval or a range. Here's another day where even with overtime, we're losing money. What happened?
You're not treating a full 10 patients.
Why not? Why didn't I treat 10 patients on this day? Only 8 patients showed up. For whom is it the worst case if 15 patients show up and the machine goes down? Yes, but I don't care about them. The staff. We're sitting in a conference room with a bunch of clinicians who wish they could get home before midnight. The days they hate are the days with 15 patients and the machine goes down. Who else matters? The CFO. Is 15 patients the worst case for the CFO? No, that's 15,000 coming in the door. What's the worst day for the CFO?
No one knows.
The day when only 5 patients show up. That's a bad day for the CFO. Is that plausible that you could sit there with a bunch of clinicians and hear worst case? Yeah. So that's the sort of substantively the problem that went wrong. Worst case analysis because they couldn't do Monte Carlo simulation, and then human judgment failed in the face of uncertainty because they were thinking about what's the worst case for us and our experience. That's not actually the worst case financially.
So then the issue with this was assumptions.
But we need way more specific. So again, is the believing they had identified the worst case by thinking intuitively about a probabilistic system. You should always be nervous when people are thinking intuitively about a probabilistic system. That's substantively what's going on. Here's mathematically what's going on. And this is the second important idea in the meta lesson. That is not linear. In nonlinear and probability creates mayhem, just like nonlinear and algorithms and optimization do. You remember the last week of the last mini, we had a problem where we located one facility just fine, but then when we tried to locate two facilities, you got in trouble, and the reason was there was a min function. The min of two bowls is not a bowl. Well, this is a little bit similar. Min function causes mischief. More generally, any nonlinear function causes mischief when you have uncertainty. So that's the second big idea, and it is there. The good news is this idea has a very, very concise representation, so it takes up only 1/2 line on your crib sheet. The bad news is it's a deep concept, so it takes a while. That's key thing. Now, I wrote it as not equals. It should really be does not necessarily equal. But by sheer coincidence, it might happen to be equal, but in general, it will not be equal. Okay. What does all this mean? The x's are our parameters, and at this point in the course, at least some of them are unknown or random, uncertain. They have distributions. The f, that's our model. That's what translates the x's into the thing we care about, net revenue in this particular case. The E in brackets is the expectation operator. Take the mean. The hospital is going to experience this day over and over again, so this is an instance in which they do care about the mean. People who haven't taken a class like this do not know how to take that expectation operator. So what they're tempted to do is plug in their best guess for all of those uncertain parameters. That's what this means. We have a model F. In the real world, it might spread over thousands of cells. We got some model of whatever it is you care about. Some of its quantities, parameters, x's, are not known for sure. They have a distribution. They should be modeled as things that wiggle. But if somebody doesn't know how to run Monte Carlo simulation, they will be tempted to just plug in their best guess. Could have 5 patients, could have 15, on average it's 10. Let me just plug 10 into the spreadsheet. That's what this is. What you're gonna do is you're gonna have a model where the x's are allowed to wiggle because you're going to represent them with random variables. And then you're going to take the expectation by running that model 10,000 times and taking the average. When you do this by Monte Carlo simulation, you're getting a slightly imperfect approximation to the true value. But if you run enough trials, it's a really, really good approximation. When you do this, you're essentially flipping a coin that has some real possibility of landing, you're fired. Because this cannot just be imprecise, this can just be wrong and way wrong. Open up from Canvas, this sheet, this 12.2C simulation for illustrating this idea. I mean, if you don't have a computer, it's fine. You can watch me do it. This is a very, very simple exercise, but you may remember it better if you actually have your hands on the keyboard. The imaging department example was real, captured real stories. Here, totally abstract. I'm stripping it down and making it as absolute simple as possible. I've got 2 x's. They're both uniformly distributed. I've got 5 outcomes that I'm claiming are super important. And for all 5, I want to understand the expected value of them. Up here, we're going to do what people who have not taken this class and learned Monte Carlo simulation would do. And then down here, we're going to do Monte Carlo simulation. And these are the functions that we care about. So in this row, will do what 90% of the world does. We don't know what the value of X1 is, but it's uniformly distributed between 0 and 1. What is its expected value? Uniform between 0 and 1, what's the expected value? 0.5. This one's uniform between 1 and 2. What's its expected value? So those are our best guesses of the two X's. And if I just copy those formulas down, paste special formula, then I've just done this. Easy, fast, seductive, fatal. Now let's do it right. So I will run my data table, 10,000 rows, pick some blank cell and recompute. Now, if I try to do this with any of these guys, how well do I do? Like for outcome, Y1. How big a difference is there between the people who went to a Podunky school with no good quantitative training and what graduates from the Heinz School find? 1.5 versus 1.504, it's not very different. Furthermore, 1.5 is actually the correct answer. The 1.504 is just a slightly noisy approximation. In fact, 1.5 is the correct answer. And for Y2 and Y3 and Y4, same story. And for Y5, is there any difference? So the people who went to the Podunky school that didn't have a good quantitative program say, cost will be about $500,000, no big deal. And then they turn out to be $3 million. Somebody got fired. What's the difference between this column and these columns? That is not linear. Now I'd like to do one that's a little more real. So on this page. Okay, so here, and literally, I'd like you guys to wait, where are we on time? 4:20. About 30 minutes. Yeah, 3 minutes. So no, I want you to do this. So we're interested in the benefit cost ratio of something. Our best guess is the program benefits will be 1,500 and the cost will be 300. So what do these people say the benefit cost ratio is going to be? We'll say 5. 1,500 divided by 300 is 5. However, there's uncertainty in the real world. So we want to model these both as normally distributed random variables with a standard deviation of 100, except, quick aside, the costs are never going to go below 0 and realistically not going to go below 50. So generate your normal random variable with a mean of 300, standard deviation of 100, and then add a little if statement. And the if statement is, if that thing's less than 50, change it to 50. And run a simulation 10,000 times to get the distribution of the possible benefit cost ratios for this program. Preview, is there any nonlinearity here? Yeah, random variable divided by random variable. There's some nonlinearity here. All right, so take 5 minutes to try to build this simulation yourself. You guys work together. So just as a reminder, you've got the workbook that tells you how to create these random variables. It's on the Canvas page from last time. So you're going to open up the template for running 10,000 trials. And if you don't know how to create the normal random variable, it is in that workbook. How to create random variables. And it's with that norm inverse function. hopefully you did something like this. Do the norm inverse, give it a rand function with this mean and this standard deviation, generate, oops. What did I do? Put the arguments in the wrong order.
Thanks.
Oh, it's norm period in.
Oh, norm has an M in it, not another N. Good, thank you. All right, so that's my benefit. That's my cost, not truncated. If, well, I can just probably do it without an if function. It's probably easier to say max of 50 and what kicked out of the random variable. My benefit cost ratio is benefit minus cost. Feed that into the simulation, run 10,000 trials. Is that 5? It's really not. That's confidence interval for it. It's well outside of 5. And that's the range of possible values. Obviously not all 5. We can so the distribution with a big whomping tail off at the end. Provide histogram. Is this bell shaped? No, that's leaning off to one side. Give a quick explanation of what's driving the shape of the distribution. Why are there some things out there?
Standard deviation of the cost is larger relative to the mean.
Standard deviation of the cost is larger what?
Relative to the mean. Does that make any sense?
Yeah, it does, but we can be more precise. Divide by 0, you get a really big number.
Yeah.
No, we're not dividing by 0 because we truncated at 50. But yeah, when you get a roll of the dice that makes the cost low, you get a small number in the denominator. When you divide by a small number, the ratio gets jacked way up. So the plus and minus the 100 in the numerator is not really driving most of it, but plus or minus in the denominator does. And when you run a lot of trials, there's some, well, even if you run one trial, there's some possibility of being 2-3 standard deviations below the mean. And that takes you down to dividing by 150 instead of dividing by, dividing by 150 instead of 300. And that knocks it way up from 5 to 10-ish. What's the expected value of the BC ratio and 9% confidence interval for it? That's just the standard read off of the results. So best guess 5.92. If you were reporting a 90% confidence interval, you'd say 3.2 to 11.4. So in the first place, your best guess isn't 5, but also there's actually really quite a spread here. And the spread is driven by the standard deviation and the cost. And I'll show that in just a second. What ratio would the naive person report? They would have said 5. Let me make the point that it's a lot what's going on in the denominator. I will make the standard deviation of the cost be effectively 0. And that didn't, we still have a big whomping spread. The spread is driven by the uncertainty in the denominator and the possibility that there's some chance that you get down to dividing by a very small number. Right. That's the main point. And that B over C, that's not linear.
The just because I missed it, the random variable goes in the value cell.
Yep. That's my thing that wiggles.
Okay.
So this is my model. This is one trial. And then when I do that, then that's how I'm running 10,000 trials. Okay, 20 minutes left. Excellent. There's one more idea, really. I mean, just a few more ideas, but there's one main one still to try to talk about. Oh yeah. Sam Savage is brilliant. He is seriously, like, IQ is probably getting close to quadruple digits, but he's also way funnier than anybody else who writes about management science. And if you want to read truly entertaining, think about decisions that are uncertain. His book is fantastic. And here's an example of where he's so clever with this. He says, let's suppose that the variable X indicates the position of a drunk walking down a busy 2-lane highway. And in particular, it's distance left, right, 0 is you're right on the double yellow line, 1 is you're over in this lane, -1 you're over in that lane, and this is a drunk. So this is a highly variable thing, but suppose the mean is 0. On average, the drunk is in the middle of the lane. And then the F function is the health of that individual. So this says, well, E of X is 0. On average, the drunk is right there on the double yellow line. It doesn't matter that there are semi-trailers going either side. But in reality, when you plug in the full distribution of possible positions of the drunk who's weaving back and forth through traffic, and then apply the truck, you're going to get an expected health state that is not altogether in great shape. That's his example. The meta story here, I would tell, goes like this. Throughout your life, you're going to sit in meetings and people are going to do this. And don't bother trying to give them a Monte Carlo simulation exercise in 5 minutes. They won't understand it. You just go home from the meeting and you create your own little spreadsheet model and you put in actual distributions for the X's and you run it. And 4 times out of 5, you're going to find out that your expected value from the simulation is not very different than this, which is to say you're going to find out that there aren't a lot of really big nonlinearities in that model in ways that interact with the uncertainty. And it's like that symphony model. It was basically sort of an added up model. It was mostly linear. Stuff that was nonlinear didn't matter very much. Doesn't mean the Monte Carlo simulation isn't useful. You're still getting a sense of the variability, but all you're doing in that case is you're making life more complicated for the boss. The idiot said, $1 million net revenue, you're coming along and saying, we should really think about between 700,000 and 1.3 million, and you just made your bosses get a headache because that's more complicated. You're not going to win the promotion race on those days. But 1 time out of 5, the idiot is going to have something that comes out like the imaging case, and their expected value is just going to be wrong. And that's when you put your hand up and say, no, we can't do it that way. The expected value is actually is truly different than what came out of this. And that's when you're the hero. And if you do that like once a month throughout your career, and 1 time out of 5, you're a hero, that means being a hero a couple times a year, it'll be a good thing. Okay, next thing is, so if it's linear, then plugging in the mean is fine. We can even do the standard deviation. This is the warning about nonlinear. We can do a little bit better, and the Sam Savage book is great with examples on this also. Like, suppose that the F function is shaped like this. So it is convex. And the X is uniformly spread along here. If we do the simple thing, then we would, well, this is F of E of X. I should stay with E of X, so consistent notation. And if you, yeah, that's f of b of x. What is e of f of x? Well, imagine throwing darts randomly along this axis. You know, like some darts will land here and you'll get this value on the vertical axis. Some darts will land here and you get this value. And now you take the average of the f of x's and you're going to get up here. So when the F model is convex, then E of f of x will be bigger than f of E of x. And so you can do the same thing that the not so smart person will do, but you don't say I've just computed E of f of x. You say I've got a lower bound on it. And it's same thing in reverse when it's a concave function. So again, imagine that x is drawn from across here. This is E of x. So I come over to the vertical axis. This is f of E of x. But now suppose instead we think about E of f of x as throw darts randomly, drawing different values of x. Some of those are going to land like here, and you're going to get this. And some are going to land here, and you'll get that. And you take the average of those, and E of f of x will be below f of E of x. And so doing the simple thing will give you a bound on the other side when the function is concave. And that's useful because sometimes you do have functions like this, like x is the error, and then this is the cost. Big errors, big costs, and then you can use that sort of bound. It's called Jensen's inequality. Okay, let me get to this idea of random sum of random variables. It's pretty common. We have instances in which we add up a bunch of different random variables, like a bunch of salespeople. We don't know how much each is going to generate in sales revenue. We're interested in the total. And there are at least two distinguishable cases, and maybe more in the twist. The simplest case is you know exactly what the value n is. You know exactly how many random variables you're adding up. That's a simple sum of random variables. And if each of the x's is IID, so all your salespeople are equally skilled calling on customers who are the same size customers, so every one of those draws is from the same distribution, then the mean of total revenue is just number of salespeople times the mean of x. And the variance of the total is just number of salespeople times the variance of the size of each individual sale. That follows directly from the principles of linearity. That's sort of straightforward. However, there's a different thing. You have to pay attention to which case applies. Sometimes the number of numbers, the number of random numbers you're adding up is itself random. For instance, suppose you've got those 25 salespeople, but these are people who are going to either make a big sale or no sale. So every one of them flips a coin to figure out whether or not a sale is made. And then if a sale is made, there's a draw from the random variable x of how big is that sale in dollar value. And now you're trying to figure out what's our expected revenue and what's the variance on the revenue in that case. That's called a random sum of random variables because the number of terms in that sum is not known. And we can face sort of the same thing at Heinz College. We don't know how many of the admitted students will come. And then each of the admitted students also has an uncertain net revenue for us because we get revenue net of tuition and the tax paid up to Warner Hall, right? In that situation, the mean of y can still be found by multiplying the mean of n times the mean of x, expected number of sales times the average size of the sale. But the variance has an extra term. This piece looks just like before. There's the variance of x, and you got to multiply it by your best guess of the number of those. However, there's also a term that has the variance of n in it. There's an extra kicker. So that's called the random sum of random variables. And here's an example that kind of forces you to think about it, but makes things even more complicated. Back to, we're launching a Zoom management program. The basic parameters are in the slide. Best guess, 20 students, $30,000 each. So mean revenue, 600,000. But we know two things. First is number of students is uncertain, and we view it as anywhere between 15 and 25, all equally like. So we'll model that with the rand between discrete uniform thing, expected value of 20. And also, everybody agrees that tuition per student can be anywhere between 10,000 and 50,000. Dean wants to know confidence interval on interview, on revenue, probability revenue is close to that 600,000. Suppose the program will cost 500,000. So what's probability that will be in the black as opposed to in the red, and what's chance that it produces a big win? Think for a minute about how you would model that. And if you can, go ahead and open up, start typing in the spreadsheet, but at least think about how you would model that. And in 3 minutes, I'll walk you through what I've created in the spreadsheet. You can talk with the person next to you. This is the kind of thing that's probably useful. Do that. What would your model look like? How would you interpret those things?
At least for the students. Tuition can be, I guess it can be anything. But also
using that, and then you would use that.
Well, the first bullet point, if we second line.
Like a trial.
Students, and then let's say 50,000. And that's gonna be 100K, and the high will be construction.
Yeah.
Then the basically we just find those with stuff. The lower. And the budget's the cost.
I don't think.
5% to 95.
Okay, let me show you two wrong ways to think about it, and then I'll show you two different simulation ways of thinking about it, which either could be right. And the meta point here is you gotta force people to think precisely. So here's one wrong model. One wrong model is to make it a simple sum of random variables, where you just say, I'm gonna pretend for sure there will be 20 students. And you say, look, it's probably going to be very roughly bell-shaped. So if I just get the mean and the standard deviation, I'll know about what it is. The mean, of course, is going to be 600. And this would be an argument for a standard deviation of around 50. You're just saying 20 students, the variance for each individual student, 133. So the variance of the sum is 20 times 133. Another thing you could do is the opposite. Say, I can't handle thinking about X and N both being random. So I'll go the other way and I'll say that the X, the revenue per student, is exactly 30. And then I will treat the revenue as the random variable N times 30, and the random variable N has this variance. And so the 30 squared times 10 gets you to 9,000, take the square root. So those are two wrong ways. I have in the spreadsheet the exact calculations, but here are two ways of thinking about it in a simulation perspective. This is our number of students, just ran between 15 and 25. Hopefully everybody would have done that. One way to calculate, and over here, I've got a bunch of draws of that uniform 10 to 50. All of these numbers here are uniform 10 to 50. Now, one way, and I've labeled it the second way, is to say, hey, when they said anywhere between 10 and 50, they meant the average. And since they meant the average, then the total is just the number of students times one draw from that random variable. That is a plausible interpretation of what people meant when they said tuition is anywhere between 10 and 50. But another interpretation is, however many students come, every one of them gets their own individual draw. And so the way to model the whole thing is trying to get a smaller number of students. Not helping. All right, 18 is fewer than I'm gonna get. So I set this. So I set this up to allow for 25 students, but then I have a little variable here that indicates yes, no, did that particular individual attend? And it's driven by that cell, which is the number of students who come. So when this is 18, I have 18 ones here. And after that, it's 0. And then my revenue is the sum product of those two columns. So everybody who does come, I add in their net revenue, but every one of those 18 students is now getting their own roll of the dice. I would submit those are two plausible ways of thinking about it. And I suspect that among the 35 of you, some of you thought one of those, some of you thought the other. But when you run the simulation, it makes a big lump in difference to the standard deviation, and hence the answer to all of the dean's questions, how much risk is going on. Model number 2 produces a much bigger spread for Y because you're only rolling the X die once. And if it happens to come out 49.9, you're in Fat City because every single one of the students is paying 49.9. If that one roll of the die for X comes out at 11, then the school is hurting because every one of the students is paying 11. With model number one, however many students come, everyone rolls separately. And you might get stuck paying 49.9, but you get away paying only 11. And that sort of averages out. So it exposes the school to much less risk. Here's the punchline. I don't think either of those interpretations is obviously the only reasonable way to hear the words revenue per student can be anywhere between 10 and 50, everything equally likely. So when you're sitting in that conference room and everybody says, yup, we agree on that, you're supposed to put your hand up in the air and say, no, you don't all agree. You're being too vague to know whether or not you all agree. If I'm going to go build this model, you've got to tell me, what did you actually mean by the statement equally likely to be anywhere between 10 and 50? Was that a statement about the average? Or was that a statement about each individual student who will get their own draw from that distribution? Because it makes a very big difference to the risk that the organization faces. You're waiting to ask a question.
Well, I guess it's specific to this example and it'll change depending on our work situations. But in this example, just knowing what we know about, maybe I misunderstand tuition, but isn't tuition the same for every student?
Well, tuition is, but net tuition is wildly different because of the size of the scholarships.
I see.
So you defaulted to this assumption.
Yes.
For a good reason, fair enough. But the overall thing I'm alerting you to is how you add things up matters, this random incidence thing. And the meta lesson is words need to be, you need to push people to be precise to make sure everybody is actually on the same page. You're hearing the expert correctly. Okay. Good luck on tomorrow's test.